morning, everybody. Thank you for being here today. I'm excited to talk to you about the essentials of hygienic welding. This will be Max's School of Welding. I'll guide you through 3A standards, materials, combustibles, welder function and welder components, preparation, do's and don'ts, inspections, and of course all things purged. These are best practices that go into achieving a finished product. With that being said, I will treat this audience as if you are a new hire, doing my best to simplify the information we are covering so you can better understand the welding process. Specifications we will discuss, 3A sanitary standards and accepted practices, a couple of areas to reference. For more info would be AWS D18.1, specification for welding authentic stainless steel tube and pipe systems and sanitary applications, along with AWS D18.3 specification for welding of tanks, vessels, and other equipment in sanitary applications. AWS is a nonprofit organization dedicated to the advancement of science, technology, and application of welding, creating welding standards, certifications, and educational programs. AWS works with organizations such as 3A to align welding specifications for hygienic applications. 3A permanently installed piping. 3A guidelines were established for milk and milk products, but now these guidelines are used for many other industries. Maximum surface roughness should be less than 32 RA, which is roughness average of you that don't know. Any permanent piping should have a set of guidelines to build for sloping of the drain lines to prevent pooling of product lines. Both manual and orbital welding is accepted. Using orbital welding, you're going to want to use that where it's possible. Obviously, not every situation you're going to be able to get a device so large to be able to go all the way around your tube and pipe, so you will have to resort to manual welding. But orbital welding is preferred to minimize your defects. Methods applied to welding of tube and pipe. The first method is utilizing manual GTAW or TIG welding, where a person has full control of the welding process in real time. Next, you will see a combination of manual and orbital welding, which we just talked about, being the primary option for most builds. And lastly, high purity welding protocol tends to utilize the orbital welding to its fullest, with the primary service focus to be pharmaceutical, biotech, and semiconductor industries. Welding processes used. GTAW or TIG is the process for both manual and orbital welding, along with automatic sheet welding. The manual welding side of TIG being highly sought after for manufacturer's point of view with the dying number of skilled tradesmen today. Orbital welders are a must for all your hygienic and pharmaceutical needs. GMAW or MIG is used mainly on the structural or non-product contacted components of the build. GTAW is much cleaner and precise, making it the main focus in the majority of what sanitary built projects are. Laser welding is a process that is used most commonly for the transferring of heat to a vessel. Typically, laser welding is used in an automated form to either do long seam welds on barrels or heat transferring jackets. So you'll see on a lot of these tanks where they have to maintain a certain heat, there will be an actual wrap around the single walled tank, and on there will be a lot of little circles, and those circles are actually welding the material on to keep it in place, but it allows some expansion, so in that way you could run your product to heat or cool the vessel. So since we're talking about TIG, I wanted to show you guys a TIG torch. Right here is the full TIG torch that somebody would be using, and that's going to be in one of your hands. Your filler rod will be in the other hand if necessary, but it is all controlled by your hand. Your hand placement will be right about here. There are a couple different components on this picture. You can see there's a gas diffuser here. That's your typical original gas diffuser, and this is a gas lens diffuser. So they're doing the same thing, they're just doing it slightly differently. The gas lens tends to flow out of a gas lens cup, a lot more direct, and where you want it, and allows you to put your tungsten out farther. If you're going to go the cheaper route with the original gas diffuser, you're not going to be able to stick your tungsten out of the cup here very far. So if you can't stick it out very far, how are you supposed to get that direct heat into a weld joint with a crevice that is very tight? You would switch over to a gas lens with a larger cup to allow you to put your tungsten out farther. So the order that these go in is you'll get a torch set up like this without the backer on here. You will put on the tungsten housing along the back here. Inside of here is your collet. You can do a split collet or you can do a fixed collet that doesn't have any split joints in it. That's what I prefer in training, because a lot of new guys in training resort to using a vice grips or a pliers just to tighten the back on because they can't quite get it to not move on them. So they think more pressure, more force, and that'll allow it to work. But what that does is that actually spins that little collet and twists it and then bubbles up the sides to not allow it to be held in place the way you want it to. That's why I go to a single piece collet. As much as you tighten those things down, you still can't break it. Manual versus orbital. Smaller projects may favor manual welding because you can use a smaller TIG unit called a mini arc, which only requires a 120 volt outlet to complete the welds needed, which you guys can see in every room you're going to have a 120. So that's what you're going to see on the majority of your installation sites. They're going to be a smaller box welder, and that's just because we have the power source readily available wherever we go. Manual welders can also prepare themselves for poor fit-up conditions such as gaps as compared to orbital welders that cannot account for the gaps. With the orbital system, your welds have a more consistent root bead with minimal color. This is because the purge process is about perfect in containing the argon flow and dispersing it without oxygen being included. Up here, you can see on the left, you'll notice the color variations are much more pronounced in the manual TIG weld, along with the inconsistent bead pattern. On the right, you can see an orbital weld that got optimal gas coverage and consistent weld edges in the inside and the outside of the weld. This is because the automatic system can identify the proper balance between gravity and surface tension during a weld, leaving it virtually flawless. Next, we'll go into material preparation. So before doing any welding, you're going to need to cut your pieces. You're going to need to prepare them for welding. When cutting tubing or piping for a project, a Fisher saw is a must-have. A Fisher saw is a type of saw that guides a spinning blade around a tube or a pipe 360 degrees, providing a clean and square cut, leaving only a small burr. After your pieces have been cut, then you need to make sure that there is no burrs on them when mating them together. I'm sure everyone in here has seen a file or used a file on your nails. Well, you can also use that on pipe and tube to get rid of the burrs. It's kind of a Stone Age method of going at it. We do have automated things that can help you out in this. A tube facer or squaring machine is just what I'm talking about. They're lightweight portable mill designed for facing, beveling, deburring, and squaring of tube and pipe 1/4 inch up to 4.5 inches outside diameter. A welder must also be mindful of the dirt and oils and mill scale and any other residues that would affect the welding processes. It is good practice to clean both sides of your weld joint 1 inch back, making sure no contaminants can be pulled into the weldment. Now let's just say a welder's doing multiple passes. So you did your initial cleanup on both sides of the weld joint. You do one pass. What are you supposed to do before you put down the next pass? You're also supposed to clean that weld. I'm not talking about taking the weld bead out, so to speak. I'm more or less saying you have to clean off the color variations. You have to clean off any oxides that got pulled into your weldment. And a good indication of those is if you see little black freckly flakes in there, well, if you put another pass on there, you just entrap them right inside your weldment, which essentially at the very end of the process, when you have a beautiful weld, it might not hold up in the long term. And that's why sometimes we go to x-raying things. And when you x-ray things, you can see those inclusions in the middle of your weld that you otherwise wouldn't see on the outside of your weld when you're inspecting them. So it's a very good practice to make sure that you're using a stainless steel wire brush that has not come in contact with any other contaminants and or a grinder with an abrasive. Manual GTA-W. Manual welding is used across the food, beverage, and dairy and nutritional industry, with the bulk of in-place welds done by hand. In place means that the components being welded couldn't be pre-assembled in a bench or on a table. And to put it into perspective, when you're doing a build, you tend to tack things together in place the way that it will be when you're done. So a lot of times what happens is you'll tack those pieces together, you'll put them on the system, you'll realize that everything lines up. What you'll do is you'll break those tacks off, bring it over to a pipe bench or a table, and you'll be able to use your orbital welding unit to latch on and allow it to go all the way around. Then when all your welds are done and inspected, then you'll put it back on there to do your in-place welds. So those are the welds that you can't really quite get that orbital machine on, or you can't utilize that machine on it. You'll go to hand weld those. Orbital GTAW welding process is commonly used on stainless steel tubing for pharma, aerospace components, and high purity systems. Larger products that you can break down sections and use the orbital welding technology tend to streamline the inspection process. Operating an orbital machine is not as challenging compared to manual welding. Basically, if you understand what weldments should look like, your training will be short and sweet. You will learn how to attach the machine to the tube you're welding and choosing the correct program to run after your piece is completely purged out. High purity orbital welding. Some key points and takeaways while doing high purity is the initial programming of the orbital unit is critical. Always use quality materials. High purity argon gas is a must. Support the equipment when using and not using. They're not exactly a cheap machine to buy. These provide optimum weld quality, and they can offer documentation so customers can get printouts of all the information, including weld settings, quality of completed welds, and variable QC data, which is becoming, I guess, more of a mainstay when using orbital equipment in the pharmaceutical world as well, because they want to see a breakdown of every weld and every possible environmental thing that could have happened to make that weld defective, I guess, as compared to the other welds. Weld qualifications test a person's ability to produce welds that meet specific quality and performance standards at any time. Typically, a bend test will be performed to test the root and face of the weldment to ensure there is no pitting or cracking that can adversely affect the weld joint. Or some installations, a welder may be asked to do pre-construction weld samples because certain joints can only be inspected from the outside. So this means that in the addition of being certified, you also need to make 3 welds that meet visual requirements inside and out prior to being allowed to weld on certain areas. So in some of the pipe racks, you can see there's runs that go for 200 feet. Well, obviously we're not going to have a bore scope or a video scope that can go down 200 feet to inspect it, or at least most people won't have that. So a good way to get around that is, as you get a certified welder in, you understand, you saw the paper that he can weld, you actually want to see it in real time. So you're going to actually have them do a couple samples for you, make sure that the interior and the exterior looks good. And as they have those samples, they can mirror those to the samples that you're going to actually weld in place to see if they have the same characteristics on the outside, they should be the same on the inside. Base material considerations. Building materials acceptable for 3A standards start at 304 level of corrosion resistance and go up from there. Duplex stainless steels contain equal parts of ferrite and austenite, resulting in superior corrosion resistance. Then at the bottom of the list, you can see titanium, which is 45% lighter than steel and can withstand extreme temperature variations and is highly corrosion resistant, but it comes with a pretty price tag. And I've done a few of them myself, welding on titanium to stainless steel sheets, and it doesn't necessarily weld too much different as far as your duplexes. Your duplexes, to put it into perspective for you guys, even if you're not going to ever weld, welding duplex, as soon as you put down that hood and you're looking through there and that light turns on, it looks like somebody threw dirt in your weld puddle. Like, it just looks dirty. You can clean up your base material on both sides, but it just seems dirty. So a rule of thumb that I tell guys, when they're coming in to weld these duplexes is treat it the same way you would treat stainless. Do the same motions, do the same patterns, and around the same heat. It will vary dependent on the user, but typically if you stay around the same as what you're going to be welding your normal 304 and 316 stainless steels, and you do the same motions, 9 times out of 10, it turns out pretty good. You lift up your hood and you're like, holy man, that is not exactly what I just welded, because I know what I was looking at and it looked like there was dirt in the puddle, but it looks clean when you're done. So just try not to get it in your head when doing those types of weldments that it is dirty, because it's just the material properties in it. Filler metal selections. So this is more the size and making you guys realize that we do have to add filler metal into the weldment. It's not something that is just done and you snap your fingers and it's there. You actually have to manually enter it, or it will go through a machine. You'll still have to set up all of your settings on your welder, so you still have some sort of control on your input of your filler metal, but when you're hand TIG welding, that is completely on the operator. Other than welding tubing, most welding applications require a filler metal be added. Some of the most common sizes in TIG wire are the 1/16, the 3/32, and the 1/8 inch, but you're not limited to just those. We also do offer a size down from this that you'll see in most welding shops, 045 wire, which can be also the same as some of your spool wire. Your typical spool wire will be 035 diameter or 045 diameter. You can go up to 052 diameter, but you're going to be welding some pretty thick stuff for that. And a lot of times in the hygienic world, you know, we try to cut costs, so your material isn't quite as thick. But that 045 wire, there's a couple different terms for it. You can call it spider wire, you can call it 045, or angel hair wire. I've heard that term as well. On the high end of the spectrum, the 1/8 inch, you can also go above that. You can go to the 5/32 rod, or you can go to 1/4 inch round bar if you really need to. But in that, we'll get into why you don't want to go necessarily so big. I keep talking about argon. Well, argon is the shielding gas that acts as a protectant around the molten weld pool, keeping the effects of the atmosphere out. This stabilizes the electric arc as well. Argon purge is for GTAW in the food and dairy industry, should be of commercial grade and high purity. Liquid argon is to be used when welding pharmaceutical. So you can see there's not a big difference in the level of argon that you're actually getting in those two, but it does make a huge difference when it comes to weld color. Argon purge process management. Initially, you will need a purge regulator or a flow meter to know how much argon is coming to your welder and to your purge setup. You also need an argon line to transport your argon. When welding the piping system, it is important that you have purge plugs or a way to entrap that purgement inside of your system. So typically you'll use a purge plug on one end, you'll feed your line in, and then on your exit side, which you're going to want to maintain that at the highest point of the build because argon is heavier than air, you can put tape or a purge plug on the other end of it as well, letting that argon recycle through there, pushing all the oxygen out. To know when you have a perfect amount of purge, a purge presence and purity indicator is helpful in knowing when to start welding. So this device measures the end result of your purging system. You put that on your exit hole of your purge system, and that measures the amount of oxygen that's present inside of your line. You're going to want that to read virtually 0 if you're going for a non-accessible weld, and you want it to be hygienic at the end because color plays a big role in that. Argon hoses is another big thing. You're going to want to make sure that it's compatible with the gas that you're using. And the past few years, we've had an issue where we have complete purge, or so we thought we had complete purge, and we're still getting these color variations. Now, one thing that can contribute to that is the humidity in your room. So making a temperature controlled and humidity controlled environment is crucial, but also the means of transportation in the line. So a lot of times on TIG welders, you'll see those green hoses that are used for MIG welders. We actually switched all of our TIG welding away from those green hoses because they're petroleum based, allowing oxygen to get in there and causing a darker color. To find the purge times for any length of pipe or tube, multiply the purge time by 1 foot by the total length of the pipe to be purged. This will achieve 6 times the volume of turnover purge. This will enable tacks and welds have the color of 1 or 2 on the AWS D18.2 color chart to meet the high purity system requirements. So again, it's very important to give an adequate amount of time for your purge to come to being completely pure. Another way to find an adequate amount of time to purge something if you don't have a presence and purity indicator is to do that multiplying equation that you see on the right. Next, we'll get into purge cups. So many of you may already know that when welding tube and pipe, you need to put backing gas inside to ensure a clean weldment. But what happens when you have a tank that is 10 feet in diameter and 20 feet tall with 10 sidewall ports to be put in? Well, I can tell you one thing's for sure, we're not going to fill that whole thing with Argon. That would be a waste of resources and extremely time-consuming task. So what we do is we use purge cups. This allows you to purge something without having to wait, but you will need a second person to help you. When using purge cups, you hold the cup on the back side and follow the orange glow around as the welding is being done. With having another person on the penetrating side of your weldment, this helps to know when you're penetrating in real time. One thing that is a common knowledge tip for guys in the welding industry is whenever you're holding your purge cup on the back side of your weldment like this, you always want to let your welder know when he's not penetrating or not getting the results that is desired. So typically what a guy will do with these purge cups, because you don't want to take it off the material necessarily, is they lightly tap on the outside of it, letting the welder know to either slow down or something is going wrong and you need to stop before we have to take the purge cup off and then it becomes oxidized. And right here you can see where the purge was held on there good, and right here where somebody must have fallen asleep being underneath the tank holding the purge. That happens very quickly, so you need to make sure that that purge cup is over the top of the weldment going on the outside at all times. And don't pull it off until that welder stops, until the glow stops. Otherwise you're going to have to go back in. Certain situation like this, you would need to first sand off that material, then back grind into it. Technically, you should use a PT test to find out if there's any other inclusions inside there before you can actually weld that seam again. Tungsten details. The choices you have for sharpening tungsten for manual welding are pedestal grinders, disc grinders, and tungsten grinders. When orbital welding, it is very important that the tungsten grinder or pre-ground tungsten is used to make sure that everything is like a machine, because you're putting it in a machine and you want the same results every single time. Another thing you can see here, this is not your ideal way to sharpen a tungsten. When doing it on a tungsten grinder, you might see somebody turning the tungsten sideways as the wheel's spinning this way. That'll get you this result, which is not ideal. You can use it. I'm not going to say that you can't make a decent weld sharpening a tungsten that way. You're just going to have a lot better results if you do it longitudinally like this in a straight down direction. That allows you to have a more precise punch power through the material to get your penetration that you wanted and not having all of that energy being dispersed over a wider section, which allows for wider weldments, which allows for more deviations in the weldment. So as long as you can keep things narrow, tight, and small, that usually keeps everybody pretty happy. Now, not only is tungsten sharpening important, but the tungsten placement is one of the most important parts. Besides having the right materials and gas, something that is in the welder's hands, but is just important, is the tungsten stick out. If you put your tungsten out too far, you may dip your tungsten into the weld pool. If you do that and stop, then you must stop immediately and sharpen it and mechanically grind out your inclusions. So if you're going through a weldment and you're holding that torch going along nice and all of a sudden you dip it because somebody came and yelled something in your ear, you're going to want to stop all welding operations, and you're going to want to obviously disconnect your welding torch off the material, and then you're going to want to take your tungsten out of the cup. You're going to want to sharpen it. Also, before you start welding, you're going to want to take a grinder and actually grind out that tungsten inclusion that you just put into your weld pool and it just solidified. As you can see here, I have some recommendations, and that's not to say that you're going to use those same recommendations, but it's a great starting point. So when doing butt joint, pipe, and tube welds, those are all basically in a flat surface. When doing them, You do go around the tube, but it still is a flat joint. You're going to want your tungsten stick out to be an 1/8 inch to 5/16 of an inch. So you're going to want it recessed in just a little bit farther. That allows for a more directionally straight penetrating versus if you tilt it back, that pushes your puddle out farther in front of you, doesn't allow it to penetrate as much. Which that's where the T-joint and the lap joint come in. You stick your tungsten out just a little bit farther outside the cup, not only for the penetrating aspect, because you technically in a lot of T-joints you're not going to per se want to penetrate, so it's not a necessity, but you are going to want to see what you're welding. And you can't see what you're welding when your torch is straight down and your material's like this. You tend to turn your head kind of like that. So if you push your tungsten out a little bit farther, then you can arc your torch back and then you could actually see what's going on in front of you. Now the distance from your tungsten to the actual piece of material should be about a 1/16 to an 1/8 inch away. I wouldn't usually pull my tungsten off the material any farther than that. You're going to want to maintain that distance. And the reason being is because then you're going to have optimal placement of your weld puddle, and the toes of your weld will be nice and lined up and uniform. You could dictate that a lot better when your tungsten is closer to the material than if it's farther away, dispersing all of that energy all over the place. There are some of the basic issues when manual welding. So wrong welding method, machine was not set up right, purge quality and time wasn't there, work environment, so high humidity, operator skill, poor material preparation, and poor fit up. So gaps. A lot of times you're going to see a nasty looking weld, or it looked good on the top portion, but on the bottom portion it got really wide and it started to sag. Well, why is that? Well, if you run into a gap, that person was manually welding it and they had to fill wire. Initially when they started the weld, they didn't have to fill wire, but then at the bottom they had to fill wire to make those materials come together. Steps to ensure a perfect weld: cutting with the Fisher saws, facing and preparation when required, tight fit-ups, purge tacking, purging your whole system, making sure the purge in your welder is going good, tungsten electrode preparation, so just making sure that your tungsten is clean and or sharp, qualifying the welders, and doing weld coupons, ensuring that they actually do understand what's going on. Weld deviations. Another key point in letting outside contaminants into your weld puddle when manual welding with filler wire is to make sure that the filler wire stays in the gas flow zone, and if it comes out of the gas flow zone, the operator will be able to tell because the filler wire will ball up on the end and oxidize almost every time. When this happens, the best thing to do is to cut off the oxidized gray or black portion of the filler wire. If the oxidized wire is then reintroduced into your weldment, and the weld puddle may act as if it wants to go all different directions, making it hard to control the progression forward of the weld puddle and ultimately damaging the oxide layer. So this is a big reason why people's welds will essentially look like crap at the start, is because they just did a weldment and they were too lazy to cut that balled up end portion off. And the reason why it balled up is because they took it out of that gas flow zone. Here are some welding hiccups. Like I said in the last slide, you're going to want to pre-purge before you do any tacks. Over here you can see a hot tack was done. Somebody didn't purge the system before tacking it together. They tacked it, they never looked on the inside to see if they penetrated through. And then they put their purge on and they began doing the weld. And you could see the weld looks great, except for that spot where they had the hot tack. That could be easily avoided if the person would have looked in there after he tacked it and used a straight grinder or something of that equivalent to get that hot tack out. Right here you could see low heat. The guy was probably cruising along, thought he had a great weld going, got too comfortable and started to speed up, which causes misses like this to happen. Low pour argon purge. You could see this one and this one have some similar characteristics here. If you have low or poor argon, like it's not quite covering it or you couldn't quite get your purging apparatus close enough to it, you're going to probably get this result. And that's not far off from the no purge result. No purge results, that whole entire weldment would need to be cut out. You would need to face back until you got out of that heat tint zone, just to be able to do that weldment again and have it actually have the corrosive resistant characteristics that it should have had in the first place. And right here you can see a lot of things happen wrong here. Poor purge, low heat, and misalignment, all a recipe for a disaster. Right here you can see the weld discoloration, heat tint acceptance limits. I'm sure all of you have seen this quite a lot. This is a chart that is widely used in the 3A, but still rings true on its importance. It's a great reference to use and to have in-house for all your welders to look at, because for your pharmaceutical needs, you're going to be around that 1 to 2 range right here. That's just a good visual thing to have around. The heat affected zone is the area on both sides of the weld bead that is most susceptible to corrosion. Factors that influence heat tint are oxygen in your backing gas causing the heat tint, moisture in the backing gas causing the heat tint, oils like those on your hands can increase the color as well. Material surface finish, you'll see different colorations dependent on the surface material finish, mil scale versus 2B versus number 4 finish. They'll all allow that heat tint to go out at different levels. Hydrogen in the backing gas can actually decrease your heat tint. In the diffuser setup that is on the right and left, the gas lens is on the right, the standard diffuser is on the left. You can see on the left it has small ports which can lead to less stable coverage under some circumstances. Contrary, the gas lens setup, which employs a gas screen, resulting in a more consistent and stable flow. The stability is key when welding stainless steel, and it will keep the puddle more stable and less wobbly, allowing for a cleaner looking weld. You can see the heat affected zone hardly change, so don't be quick to judge a weld by its appearance and color. Rather, the heat affected zone and the weld quality and its shape and consistency. So the same welder welded both sides of these, just using different components on the welder. He used the same parameters and everything. You can see the heat affected zone is virtually almost the same. But he was able to make a prettier looking weld over here, and I'm sure he liked the outcome a little bit better as well. In price comparison, I believe, but don't quote me, these are probably about 4 times the price of these when it comes to the components. Visual weld acceptance criteria, ID and OD. Welders must have full penetration, good alignment, offset not to exceed 10% of the base material thickness. So there is some offset that you are allowed, but precision is key. No cracks, undercut, crevices, or embodied or protruding material. Uniform weld space, weld bead, and entire circumference. No visible defects, cracks, porosity, slag islands, minimal weld discoloration, no underfill, excessive penetration. All welds to be continuous with no skips. On the right here, you can see the interior of the weld. Now, you're not going to see that on the outside layer, but it is on the inside layer, so that does highlight the importance to make sure you're doing the right thing as you're doing the welding. Visual inspection choices. Like I said before about running a borescope down 200 feet of line, that's not really a choice, so to speak. But borescopes, they do actually have pretty long lines on them, so you can access quite a bit of weldments. And with that being said, a lot of times they'll have split joints in systems, so in that way you can actually break them apart to use your borescope to get down in and actually see the welds in that section of it. In person, flashlight, mirrors, they work great, or a video scope, which is becoming a very popular choice by customers because it can actually play that back in real time for you about what you just saw. And a lot of customers like that because they don't really necessarily trust everybody. We're going to talk about sheet metal welding, not only just the tube and piping side. Make sure all welds are continuous, no skips or voids that can possibly get pulled or trapped on. That's obviously a must. When welding sheets together, an outer wrap of a tank, legs, brackets, nozzles, baffles, and repads, the information thus far applies. These are some finishing applications that you will probably see on the finished product. I'm not going to go too far in depth with the time frame that we have, but everything looks shiny, right? It doesn't just come out like that unless you buy the sheet material that is a number 6 or number 4 sanitary finish, but otherwise the welding here, somebody ground on that after it was welded. When doing welding, Heat sinks is another big thing that helps you out. Maintains roundness and shape, reduces heat input to the fitting. The main reason that they're used is to prevent distortion during any of the welding process on fittings such as level sensors that need a perfect sealing surface. Like the last gentleman was talking about, we need that nice perfect sealing surface, so this is a good way to keep that sealing surface nice. Different things that you can do on fit ups. If you have a radii on a tank, before you're going to do your build, you're going to want to look at the specifications. Now, if you can tell that your interior corners are going to need to be to a 3/16 radius, something that you could do differently when putting a nozzle in is you can actually recess it out to a corner-to-corner weldment as long as your quality department is okay with it and it passes all the specs. So then that way you can fit it like this. Your weldment becomes already radius for you, so the grinding application doesn't necessarily take as long. Right here's a MIG failure. Absolutely atrocious. So this is highlighting the importance of backing gas and making sure that you have the correct backing gas for the application. Here they used the wrong backing gas and they had two other alternatives that they could have used in place of it that were right next to them. But their inexperience level shows that they had no clue. Eliminating gaps. Like I said before, orbital welders like a tight fit up. Well, so do manual welders. We like a tight fit up a lot better than gaps. So there's many different things you can do when using stainless steel and making the gaps disappear like magic. Shrink welding, ball peen hammer. I don't advise that if it's going to be visually seen portion, because it'll look like somebody took a golf ball to a driving range and just pinned it off the tank. Half clamps, if you clean it up afterwards, ratchet straps, chain hoist, closed tacking, facer, and turnbuckle. Right down here you can see there was an abnormally large gap. I used the welder to do a shrink bead right below the weld seam, allowing for that material to curl in, creating a tight fit up. When adding filler metal, the most important thing is to not do a dab move, but more or less dab your filler rod into the weldment. Now when doing that, you're going to want to make sure that you don't pull that filler rod outside of the gas flow zone. If you pull it out of the gas flow zone, we're going to go back to that balled up filler rod that you saw on the other side. When doing this, it is very important to dab. Reason being is if you lay the wire down like this and walk right over the top of it, if you don't have enough heat and the guy's just cruising along, he does melt this top layer of the wire, but the bottom layer keeps its shape and then it makes a void right behind it. So always dab, not dancing dab, but dabbing your filler rod. Down to the last slide here, techniques of manual TIG welding. You could walk the cup, you could freehand, or you can step. Now down here, this whole area with all these awesome designs, these are walking the cup. Just a bunch of different patterns that guys will do. One thing that I want you guys to take away from this and maybe try in your hotel room or do it at home is, you hand me that water bottle? Take a water bottle like this, drill about a 3/16 hole in the top, stick a number 2 pencil up through it, or pen, whatever you prefer. Stick it out about a ½ inch. And then take a piece of paper, draw a line on that piece of paper, put just the edge of the cap down as if it would be your cup. And then the pencil coming out is your tungsten. Put that down onto your material like such, holding on to the back end of your bottle, and start trying to make those patterns down at the bottom of the slide. Now if you can do that and make those patterns, chances are you're going to be a pretty good welder. If you grab onto this bottle and you start and you squish it and crunch it, most likely you're going to have a difficulty time starting to weld because that's showing you're gripping that thing way too tight.